So, hello everyone, and welcome to Spectral Geometry in the Clouds. Today it's a pleasure to listen to Julien Moy, who will tell us about the spectral statistics of negatively curved surface covers. As usual, if you have questions during the talk, don't hesitate to unmute yourself or ask them in the chat. We will relay them to the speaker. So, yeah, Julien, the floor is yours.
Thank you, Laura, and thanks to the organizers for the invitation. So today I want to discuss some results on the distribution of eigenvalues of the Laplacian and some negatively curved surface covers. So I will explain this in the motivation comes from eigenvalues of the Laplacian on surfaces. So to fix the ideas, we'll work with a closed Riemannian surface. So in dimension 2, I assume X to have no boundary. And in this case, the spectrum of the Laplacian is known to be given by a non-decreasing sequence of eigenvalues that goes to infinity. And so our goal in a very broad sense is to understand the statistical properties of the sequence lambda I. So I will explain what I mean by that in the following. But the first result on the distribution of eigenvalues, and probably the most important in the field, is given by the Weiss law, which was proven on manifolds by Levitin, I think, which tells you the following. So you are interested in the number of eigenvalues in a window that starts at lambda and stops at lambda plus w. So w is the width of the window. And Weiss law tells you that the number of eigenvalues in this window is somehow linear in w. There is a geometric factor given by the volume of x, which is rather the area here. And there is a remainder, which is square root of lambda. So it is kind of silly to look at this when w is too small, but we still have this. Okay, but then a natural question is, what about finer statistics? And can we tell more about the spectrum? So there is a conjecture that actually comes from the physics literature, which is called the Bohigas Giannoni and Schmit conjecture. These people are physicists, and they're interested in the spectrum of some quantum systems whose classical limit display some chaotic behavior. So the way I am stating their conjecture is not the way it is written in their paper, which was considering general dynamical systems. But in our setting, what they suggested is that in the situation where X has a chaotic geodesic flow, the high energy spectrum of the Laplacian should somehow display fluctuations that look like those of large random matrices. So we'll explain this in the following. So the conjecture is expected to hold in the regime of high eigenvalues. So there is a plot that I extracted from the paper in 1984, and what is plotted is a function p of x. So what is p of x? What they did was computing numerically some eigenvalues of the Laplacian, not on some compact manifold, but on the stadium. So the stadium is like two half disks and stick together with a rectangle. And they could compute some eigenvalues. And what they did is they plotted the spacings between two consecutive eigenvalues. So they did this plot. And what they found is that this plot somehow agreed kind of well with what happens for some large matrices of an ensemble of random matrices called the Gaussian orthogonal ensemble, which is the curve in black. And there is another curve called Poisson. What it describes is what would happen in a situation where the spectrum is completely uncorrelated. I mean, this function Poisson is just decreasing exponential, okay? And it is what happens if between two consecutive eigenvalues, what you have is just a random jump, okay? So I need to explain a bit about random matrices now, I think. So random matrix ensembles were introduced originally, I think, in the 50s. And the goal was rather to study the spectra of large nuclei in nuclear physics. And the thing was that it was rather complicated to compute the spectra, because when you have a lot of protons and neutrons in a nucleus, interactions can get very complicated. And there's a physicist, Eugene Wigner, who suggested that instead of looking at all these complicated interactions, we could just imagine that these are given by random variables. Of course, this assumption had no physical justification, but what it made possible is doing some computations explicitly with this. So it was useful and ended up being quite powerful, actually, to conform with what experiments showed. So there are mainly two ensemble of matrices I want to discuss. The first one is the Gaussian orthogonal ensemble. So you take random symmetric matrices, and what you put is Gaussian variables on all the entries. So this is not the same variance on the diagonal and on the non-diagonal coefficients. This is for some normalization purposes. And this ensemble is used to model some time-uniform invariant systems. The reason it is called orthogonal is that this ensemble, and especially the probability measure on this ensemble, is invariant when you multiply a matrix by an orthogonal matrix. There is. And there is another model of random matrix that is used to describe quantum systems that are supposed to break time reversal symmetry. So what you do is you take not symmetric matrix, but Hermitian matrix. So I forgot to say, but S and A are real. So here you take Xn that is S plus IA with A antisymmetric, and you put also Gaussian laws for the coefficients of the antisymmetric matrix with these conditions. And what is quite formidable with these random ensembles is that one can write down explicitly the density of eigenvalues for both these models. So it is pretty easy to make some computations on the spectra, provided one accepts to perform some computations on average. Okay, so in the slide before I talked about chaotic geodesic flows, so I need to explain this. So we will work on surfaces that have variable negative curvature. So I don't ask the curvature to be constant, but I ask it to be negative. And the surfaces enjoy some nice properties in this context, which is that the geodesic flow is strongly chaotic. So what the geodesic flow does is that it takes a point on the manifold and the unit tangent vector of the manifold, and then it just follows the geodesic that has this unit speed for initial condition. And when the manifold is negatively curved, we have strong chaotic properties that can be roughly stated in saying that there are some contractions in phase space, some expansions too, and also folding due to the fact that the manifold is compact. And in negative curvature, we will be interested in next in the closed orbits of the geodesic flow. And it happens that the number of closed orbits of this flow grows very fast. Actually, is good. What I denoted by J is the set of closed orbits of the geodesic flow, and the number of closed orbits that have lengths is smaller than L grows exponentially fast with L. What I denoted H top is the topological entropy of the geodesic flow, which is not so important here. Okay, so this is the setting in which we will work. And before going on, I would like to explain how we will understand the Bohigas Giannoni and Schmit conjecture, because it was stated kind of broadly. And we'll look at a very particular statistic for the eigenvalues. So what we do is the following. We take some function f with some technical hypotheses, which are that f is smooth, it's an even function, real, and we assume the Fourier transform of f to be compactly supported. And when this is done, we take some numbers lambda, think of it as a frequency, and L, which should be thought of as a time, actually, inverse frequency. And we look at this new function, h of lambda L, that takes these two parameters. And with this function, we will introduce a smooth counting function for the eigenvalues of the Laplacian. So actually, what we will count is not eigenvalues of the Laplacian, but square root of eigenvalues of the Laplacian. For technical reason, it is easier to work analytically with the square root of the Laplacian here. And so I put a graph of what h lambda L is. So you have somehow a smoothed version of a sharp window centered at lambda and of width 1 over L. So there is another part in h lambda L which I do not draw, and it is of less relevance here. Okay, so we look at that. And then we have a version of Weis' law for this smooth counting function, which is that essentially, well, you have to specify a regime of lambda and L to work in, but at leading order, you still have the volume of x as a geometric factor, then lambda over L, and you multiply it by the integral of f over R, which is nothing but the Fourier transform of f at 0. And so a natural question that may come now is, to what extent does this counting function fluctuate around the prediction of Weis' term? So to study this question, we will introduce the following quantity that is called usually the spectral number variance. So we decide to average this difference squared around some interval of frequencies from lambda to lambda. Of course, the choice of lambda and 2 lambda is arbitrary. I could take lambda and 7 lambda. Doesn't matter very much here. And typically, if the fluctuations around the Weil term are small, we expect the number of variance to be small too. Okay, so this is what we will study in the following. Actually, we don't know many things about this number of variance, but there is a heuristic argument in the physics literature that is due to Michael Berry that allows to perform at a very heuristic level some computations and try to guess what it may look like. Random matrix theory, if you look at the smooth number variance for random matrices, you find that it should saturate a finite value when you take lambda large and L large in a certain regime. It wouldn't be the case if you were to look at a sharp counting function, but when you take a smooth counting function, you expect a finite value in this limit. So I want to explain the computations that Berry performed, it was in the 80s, to try to compute this number variance. So what Berry did was using semi-classical or called Gutzwiller trace formula in the literature. Usually, people may be more familiar with the Selbach trace formula, which is an exact trace formula in constant curvature, -1, that relates the ensemble of eigenvalues of the Laplacian on a closed hyperbolic manifold to the set of lengths of closed geodesics of the manifold. Constant curvature, this formula is exact. It turns out that there is an analogous formula in variable curvature that is not exact and requires working in the large lambda regime. So you have to go in the large frequency regime, but you still have something. And essentially, n of lambda L can be expressed as a Weil term, as I told before, plus some oscillating sum that I wrote here. Okay, so the difference between the true counting function and the Weil term is given by a sum of a closed geodesics. And what does it look like? There is a dynamical coefficient that I denoted A gamma. I won't explain much on this. That is related to the instability of the periodic orbit. Then there is some cosine of lambda L gamma, which oscillates very fast with lambda, especially when the lengths are large. And then there is the Fourier transform of f evaluated at the length of gamma over L. And here I want to point out that since the Fourier transform of f has compact support, here the sum is supported over a finite number of terms. As we said before, closed geodesics form a discrete set, and the length is 2. Okay, so using this semi-classical trace formula, we can rewrite to some error term, the number variance as some average of the square of the oscillating term sum. And then what Berry said is that we can perform a so-called diagonal approximation. So in the integral, when you take the square of the oscillating term, you get some cross products, some products between the cosines. And the cosines oscillate very fast and may hope that the products average to 0. There are some obvious pairs of geodesics for which this does not happen, which is when they have the same length. It happens when you take two geodesics which are the same, or when you take two geodesics that are the inverse of one another. So I denote gamma inverse a geodesic traveled upwards. Of course, let's be clear, then there may be other pairs of closed geodesics with the same length, but well, Berry said we perform this approximation and we only keep these pairs. And if you do this, you just keep these pairs. You take the square from the average, the cosines average to 0 or 1/2 when you take the square, and you are left with this sum of the closed geodesics. And already you can notice that it is independent of lambda. So this step was highly non-rigorous. However, now this quantity here, the last sum of the closed geodesics, can be computed rigorously by tools from dynamical systems. So essentially, this is related to some equidistribution properties of closed geodesics in phase space. I don't think I will have time to explain this computation, but what is quite impressive is that it can be computed and you find some limit when the length goes to infinity, L, that is independent of the surface that we were working on. And what is nicer is that the limit which that we find is the variance that one obtains when computing the smoothed number variance for the Gaussian orthogonal ensemble. So this could be very nice. Unfortunately, there are some issues. Well, the first one is that, of course, there is no justification for the diagonal approximation, and currently we lack some knowledge on the set of lengths of closed geodesics to be able to do anything. And even worse, there's actually a negative result of Liu and Sarnak, who studied the non-smoothed, actually it was the sharp counting function, the number variance for arithmetic hyperbolic surfaces. So the surfaces are hyperbolic surfaces that enjoy a lot of symmetries that are kind of exceptional in this regard. And Liu and Sarnak showed that the number variance cannot match that of GOE for all ranges of lambda and L in some way. And actually, this is not so surprising, and the fact that it doesn't work is due to the fact that these surfaces, on these surfaces, there are many closed geodesics that share the same length. Actually, it's exponentially, an exponential number of them when you take respect to the length. So, well, this is obvious on the surfaces that the diagonal approximation could not work. Well, anyway, the computations that we performed were kind of seducing. So an idea may be to find other mechanisms to make the diagonal approximation work rigorously. And one idea is to work with random surfaces and hope to gain something by performing some averages. So there has been some work recently. I want to explain the general framework. So essentially, one works on an ensemble of surfaces that I denote M, and we put a probability measure on this space. Then the counting function that we defined for the surface X becomes a random variable in M. And we will look like a slightly different quantity than the spectral number variance, which is the ensemble variance of the counting function. So we do not look at fluctuations around the value term, we look at fluctuations around the ensemble average. This is kind of different, but this is the quantity we'll look at. Okay, so what has been done recently? There has been some work on the moduli space of hyperbolic surfaces of tennis G with the Wright-Patterson probability measure. I won't discuss it a lot. And there has been some work recently too on the ensemble of n covers of some fixed surface endowed with uniform probability measure. So I will explain the second model of surfaces. This is the one I worked on. So this model of random covers, you take, as before, a surface of negative curvature. It doesn't need to be constant. And then you let Mn be all the Riemannian coverings of degree n of x. It turns out that a cover of x of degree n is labeled by some homomorphism of groups from the fundamental group of x to this permutation group over an element. And actually, the fundamental group of x is finitely generated, so there are only a finite number of such morphisms. So one can just put the uniform probability measure on the space of homomorphisms. Okay, well, how, in fact, one can build a cover of x? Well, you can just take n copies of a fundamental domain of x, and instead of gluing the edges of the copies individually, you can glue them together. So there is some freeness in this. And you have, of course, there are some rules to follow to glue the edges, but this is how you get a cover. And when you have a curving of x, any differential operator on x lifts to a differential operator on xn. Okay, so in particular, the Laplacian lifts to xn, but of course, you could have defined a metric on xn by lifting the metric over x and define the Laplacian associated to this metric. This gives the same operator. Okay, so what has been done recently on the variance? So there has been some work of Rudnick in 2 years ago, maybe 3. So Rudnick worked on the Wright-Patterson model, and No, 2 years ago too, worked on the model of random covers when x has constant curvature -1. And for both this model, one gets the following. They computed the limit of the variance where the genus or the degree of the cover, depending on the model, goes to infinity. This limit converges. Then they took the limit when L goes to infinity, and they found the value of the variance for the Gaussian orthogonal ensemble. And I point out that in their result, lambda is fixed. It is due to the fact that in constant curvature, one does not need to go to high energy regimes to make trace formulas work. So they didn't need to go to large lambda. But L had to go to infinity. So a few remarks. The first one is that No also considered some systems that break time reversal symmetry. This is done by treating the Laplacian with some unitary characters. And in this case, one finds a limit that is half the GOE value of the variance. And this is actually the variance for the Gaussian unitary ensemble of matrices. And recently, Markov and Monk adapted the Wright-Patterson formalism to study twisted Laplacians, and they also recovered the GUE result. And also, the theorems of Rudnick and No concern the variance of the counting function. One could look in principle at higher moments. This has been done for Wright-Patterson. This is a work of Rudnick and Wigman. And for random covers, this is a work of Mouse. So they obtain central limit theorems for the counting function. Okay, and 2 years ago, Frédéric No gave a talk at this seminar online thing, and he asked whether one could extend his results to the case where the base surface X has variable negative curvature. So this was the first work in my PhD thesis. And the result is yes, but there is some price to pay in the statements of the results. So I still work with closed surface with variable negative curvature, and I take the model of random covers of X. So in this case, there is an analogous result, which is kind of uglier to state. The first thing to note is that one has to let lambda go to infinity. As I explained, we work in variable curvatures, so we need to go to the high frequency regime to have trace formulas work. So we need to take lambda large. L also need to be large, but there is some regime of lambda and L that requires working with L smaller than a small constant times log of lambda. Essentially, this is due to the fact that we use some semi-classical approximation. I mean, we approximate quantum dynamics by classical dynamics, and this usually works up to some what is called the Ehrenfest time in quantum chaos, and this is something logarithmic in the frequency. Also, there is another thing required to be performed, which is a small energy average of a lambda, in which case we don't recover the GOE results, and so we have to average the energy or the frequency, if you prefer, on a small window of frequencies. But anyway, in this new regime, we recover the result. Of no. Okay, so it is also possible to include the case of twisted Laplacians as in no, and one finds the GUE result. Okay, so I want to explain how the diagonal approximation is made rigorous in this case. We do is use a semi-classical trace formula for the square root of the Laplacian on a random cover of X. So a similar trace formula I found in a work of Jacobson, Puff, and Porterovich in 2006, which they used to find some lower bounds in the remainder in Weiss law. Okay, so what does this trace formula tells us? Well, essentially the smoothed number of eigenvalues in the window is given by a value term, and then there is, as before, a sum of a closed geodesic. But the sum runs over a closed geodesics of the base surface X, okay? And this is essentially the same formula as before, but there is a new factor, which I denoted Fn of gamma, and what it represents is the number of lifts of gamma to Xn which are closed, okay? Essentially, when you take a closed geodesic on X, you can always lift the path to Xn, and there are can lift a base point on gamma to n base points on Xn. But then the path you get by following continuously a lift doesn't need to close. Okay, you just end up on another lift of the base point. So Fn of gamma counts this number. Okay. So essentially, when you have a closed geodesics, it induces a permutation on the fiber of a base point. Okay. Good. So once we have this formula at hand, we use the same asymptotics for the covariances of these random variables. Okay, Fn of gamma is of course a random variable because it depends on Xn, which is random. And essentially one could understand that the random variables Fn of gamma and Fn of gamma prime, when gamma is different of gamma prime or its inverse, they become uncorrelated in the large n limits. Okay, and this is what allows performing rigorously a kind of diagonal approximation. And here, the non-diagonal terms are killed by computing the variance of the cover. Okay, and of course, yeah, I didn't mention it, but the value term is independent of the cover. It only depends on n. So when we will compute the variance of the counting function, this value term will just disappear. Okay. So I just wrote it there. And then it remains to study the diagonal contribution. This is what I explained before. And with a bit more detail, this is a problem of classical dynamics. And it works using some trace formula for some transfer operator associated to the classical dynamics. I will not expand too much on this. Okay. Well, now I would like to explain how to break time reversal symmetry by introducing some magnetic potentials on the surface. So we started with the geodesic flow, which is a nice time reversible system. When you reverse the direction of the initial speed, it's like reversing the time. Okay. Now we look at a new operator, which is a magnetic Laplacian on the surface. So it amounts to taking some magnetic potential, which is formally a smooth section of the tangent bundle of X, so it is a one form of X. And we assume that this one form is closed. Okay, and what it means is that the magnetic field vanishes on the whole surface. Okay, so this is possible in some cases when the geometry is non-trivial. And then we consider the magnetic Laplacian, which is self-adjoint operator that I described here. And this magnetic Laplacian, okay. Yes, so two remarks. The first one is that the magnetic field vanishes. So the classical dynamics are left unchanged. The classical particle doesn't see any magnetic field. However, you can have B equal to 0 and A non-vanishing. So during the quantum evolution, some phases are added to wave functions. This effect is called the Aharonov-Bohm effect in physics, and I found this nice picture on Wikipedia, so which explains what may happen. So what it represents is a double slit experiment, but one introduces a magnetic field near the slits. And here, the classical trajectories of electrons do not meet the region where B is non-vanishing. However, there is a magnetic potential A that turns around, like the red arrows, that adds phases to the wave functions. And so on the screen, the interference pattern tends to be modified by the introduction of the magnetic potential, even though the classical trajectories never meet the region where B is non-zero. Okay. So, well, this exists in nature, these kind of situations. And so when we work with the magnetic Laplacian, well, this operator also lifts to an operator on a cover of degree n, which has a spectrum, a non-decreasing sequence of eigenvalues too that are positive. Okay. And again, one may look at the counting function of eigenvalues for this new operator. So that I denoted n of xn, so it takes three parameters, lambda, L, and A, which is the magnetic potential. And there is a very similar trace formula in this context. We still have a Weil term as before, and then this is exactly the same formula, but one has to add some phase to the formula. So there is a new term for the geodesic gamma, which takes an exponential of minus I, and then the integral over the closed geodesic gamma of the magnetic potential should be thought of somehow as some magnetic flux that goes through the surface enclosed by the geodesic gamma. Okay, of course, I said that there is no magnetic field on the surface, but you could imagine to have some magnetic field going through the holes on the surface, but still vanishing on the surface. And then if you take a curve that grows around the hole, then it could gain some flux from a magnetic field that goes through the hole. Okay, so two remarks. The first one is that when you travel geodesic backwards, the flux through the geodesic backwards is the opposite of the flux on the first geodesic. And second point is that some of you may be more familiar with Laplacians twisted by some unitary characters. So these pictures happen to be equivalent here, because when you have a flat connection on X, you can associate to it a unitary character that is defined by taking the integral of the one form of a closed curve. Okay, and it happens that this is well defined. Okay, and then what happens when you twist the Laplacian with this magnetic potential? So we make an assumption on the magnetic potential, that is that there is one closed curve, one closed geodesic, such that the integral of the potential over gamma is not an integer multiple of pi. So this actually amounts to asking that the representation rho that I define here is not plus or minus 1, essentially, okay? Or the square of rho is not equal to 1. Okay, and with this hypothesis, we have a similar result as before, but one finds in the limit the variance for the Gaussian unitary ensemble. Okay, so when we break time reversal symmetry with magnetic potentials, we recover the result of GUE. So no magnetic field potential, sorry, you find GOE. When you put magnetic potential, you find GUE. Question. By letting A depend on lambda and L, for example, can one observe all values between GUE and GOE? The answer is yes. And there is a scaling parameter that allows you to do this. And it is to take a magnetic potential of amplitude of order 1 over square root of L. And there is some parameter alpha that I didn't take here between 0 and infinity. Okay, so essentially what you do is letting the magnetic flux through closed geodesics of length of order L be of order 1 on average, okay, of order alpha, right? So we can do this and perform some computations explicitly, actually. And one finds the following. So you take the limit of the variance average, again, of the energy, take the limit of high energy and all, etc. And this can be computed, and one finds some function that is completely explicit, sigma squared, that depends on alpha, that decreases continuously from sigma GUE squared to sigma GUE squared. So, of course, alpha equals 0 amounts to, considering the situation where there is no magnetic potential, so one recovers the GUE result. And when you increase alpha, it amounts to looking at magnetic fluxes of increasing intensity through closed geodesics. And then there is a continuous transition from GUE to GUE when alpha goes to infinity. Okay, so I want to point out that there is an analogous way to break time reversal symmetry in random matrix theory. And it was done actually quite long ago. In the book of Pandemeta, this is done. So the one breaks time reversal symmetry starting from the Gaussian orthogonal ensemble. So by adding a small random antisymmetric matrix to GOE matrix. So this is, if you remember what I explained at the beginning, when we looked at GUE, we had 1 over square root of 2s plus 1 over square root of 2ia. Here, instead of doing this, you take a small coefficient in front of a. And with this, you can recover, when alpha is the correct scaling parameter, a transition between GOE and GUE for the number variance. So what I did was motivated by work of physicists, Bohigas, Giannoni, Orsay, and Schmit. in 1994, and they studied the similar symmetry breaking by adding some magnetic fields on some diodes, and they performed computations following the heuristics of Berry using a diagonal approximation. And they also identified a continuous transition between GOE and GUE. Okay, and actually, this is a remark that they do in their paper, which I found pretty relevant, which is that if one aims at checking the Bohigas Giannoni and Schmit conjecture numerically, one has to check numerically this transition too. Okay, so this gives a new way to diagnose statistics from a random mathematics theory by checking that this transition between GOE and GUE happens continuously. And there's a question that came to my mind when I prepared this talk, which is about what can be said about the spectral statistics of the magnetic Laplacian when the potential is picked at random. Okay, so you work on a fixed surface, and you take the potential at random. Okay, so well, maybe it has been done, but I'm not aware of it. But it would probably require, to some extent, working with not unitary characters of the fundamental group, but instead work with random unitary representations of the fundamental group and try to get some results in the limit when n is large. So this is the question I'm wondering about. And I think I will stop here. So thank you.
Thanks a lot, Julien, for this talk. We have some time for questions now. So if you have any questions, either unmute yourself and ask them directly or put them in the chat.
So thank you for the great talk. I was wondering, so you assume your surfaces are negatively curved. Did you assume that they're pinched, or can you deal with the curvature being somewhere, for instance?
No, you don't have to assume pinching, but well, the surface is compact, so you can have some arbitrarily large pinching, of course. Well, I didn't try to study what happens on compact settings, so maybe in such cases one needs some pinching, but well, these are some interesting questions, but probably challenging on the analytical side of the story. So
do you see a bit like where the impact of the values of the curvatures in your estimate, or are they?
Yes, you do. When I talked about the regime of lambda and L, in which the trace formula holds, it was here. You have some regime of L and lambda, and essentially the proofs rely on some approximation of the quantum dynamics by the classical dynamics, and this works up to something that we call the event first time, and it is more or less related to the entropy of the geodesic flow. And in turn, the entropy of the geodesic flow can be controlled lower and upper bounds by some bounds on the curvature. So yes, with some work, the constant C here can probably be estimated in terms of curvature upper bounds or something like that.
And I probably there's no hope in this setting to not have to take a high energy limit, right?
Yes.
There's zero hope of that.
I'm not even sure that numerically you expect to have some universality in the low energy regime.
You have time maybe for some more questions. I see unmuted microphone, so I'll let you go.
Julien, if you want to go first.
Sure. If we want to really speculate, since I see Stefan Nonnemacher is lurking somewhere here, have you thought of averaging over lots of negatively curved metrics. I mean, you mentioned the Peterson ensemble, where you average over all constant curvature metrics. But you have a much richer family of variable curvature metrics, and it would be great if there's some way to average over them and recover such results. I know Stefan, when he was your age, had tried to do this, but now it's time to revisit it.
Yes, I don't know what natural family you are referring to. I mean, we can multiply constant curvature metrics by some fixed informal factor, right?
Right.
I mean, the difficulty is to find some averaging formula for closed geodesics at some point, right?
You need to find a way, a measure.
Yeah, you need a
Space of
measure
all
too.
variable curvature metrics is an infinite dimensional space.
Yeah, and this is not very clear
Either to
me
find a finite dimensional subspace where you can perform the averaging, or to find some way to average over some infinite dimensional space. I have no idea how to do this.
Yeah, me neither.
Tried a lot, but that's
Yeah.
worth thinking about.
Yes, definitely.
I mean, you can put some infinite dimensional Gaussian measures, but we tried a little bit with Lior, but yeah, I'm not sure if it helps. But we have some papers in constant curvature with Igor Bigman and some other.
Okay.
And like fixed volume form, which
So I presume you can do higher moments here, or you have done it.
Yes, definitely. You can do higher moments, and you can do the thing about the moisture fluctuations too. But this is more or less the same story as in constant curvature from an Purvis was done in the work of Mouse. Essentially, what differs again is the difference trace formula, and of course there are some remainders to estimate in the proof, and you have to work in variable curvature, but at the end you get the same results. Yeah.
Thank you for the question, Zev. Dima, do you still have a question?
Yeah, well, it's another silly suggestion. We have an old paper with Steve Zeldich where we show that in dimension 2, if you add electric potential, then the spacings do not change. But this is only in dimension 2, and
yes,
because of scaling, things do not work in higher dimensions. But maybe if you make potential random, it's probably easier than magnetic, the question that you mentioned at the end. But maybe if one looks at random, can one do anything with random potentials, but in dimension more than 2? So perhaps this is easier than averaging over spaces of metrics.
Yeah, I didn't think of it very much so.
But,
thank you. Dima, do we have other questions for Julien at this point?
Hi, Julien. Can you extend your result to the Dirac operator?
I mean, I'm not very familiar with Dirac operators. Thing is, once you have a trace formula for your operator, it probably looks like the same when you lift it to a cover. So, I mean, I would have to look at what the trace formula for Dirac operators look like, which I don't know actually.
I think Laura is an expert on it by now.
I wouldn't quite say experts, but indeed in the article which we did with Jens, it does work exactly the same with Dirac. There's really no additional complication because you have a very similar trace formula and you can do everything in a similar light. I don't know about variable curvature though. So
yeah, there's probably some classical trace formula in the setting. I don't know if it's all that
they certainly exist in the physics literature. I think probably Jens Bolte and people like that have written down
Yeah.
something like that.
Thank you.
I mean, the trace formula for Dirac is the frame flow, right? With parallel transport along the geodesic flow. So it becomes a little bit more interesting. But it should be some.
Thank you, Timo. Do we have other questions for Julien today? All right, well, I think we can conclude this session of the Spectral Geometry in the Cloud seminar. We will announce this week the speaker for the next. We had to reshuffle things a bit right now, so we'll see each other next week at the same time with a speaker to be announced. Thank you very much for being here today, still.